Okay, let's try to address the other questions. 2. What is the approximate yield stress, excuse me. Well, you know that the yield stress is on this graph, and it's where it permanently deforms. And as we said in the problem before, it's not exactly clear if it's right here or at the top or over here, but pretty much where it deviates from linearity is probably where the yield stress is. So probably somewhere, let's call this 2,500 megapascals. So that would be 250 megapascals. Then the next question, when a load of 1,000 newtons is removed, how much does the specimen contract in length? So this is a bit of a tricky question. You're starting with the presumption that you have the sample in tensile load, and the load on this thing is 1,000 newtons. So that corresponds to some sort of strain, and the question is, when you remove that load, what was the strain? Because that is that's the amount of strain that was on the specimen with that 1,000 newton load, and the question is about how much does it contract in length. So that contraction is related to the strain, because we know the strain is equal to the change in length over the original length, and this question is about this value, delta L. Okay, so we need to know the strain at 1,000 newtons, and we get that by recognizing that this 1,000 newtons on this cross-sectional area results in a stress. It's most likely an elastic stress, but let's go ahead and compute that. So is it less than 2,500 megapascals? Let's go ahead and do the computation. I'm going to get rid of this guy over here. Okay, we have a stress of 1,000 newtons divided by the area, which is pi times 5 times 10 to the negative 3 meters squared. So here is the radius squared times pi, so that is the area. And this is equal to 1,000 newtons divided by 25 pi times 10 to the minus 6 meters squared. And I'm going to reduce that to, let's see, 1,000 divided by 25 is going to be, what is that? Is it 40? 40 times 25, 4 is 100, yeah. So 40 over pi times 10 to the 6th newtons per meter squared. Pi is like 3.14, so that's going to be, I don't know, 40 over 3.14 is about 13. We're going to call it 13. It's more than 10. So it's about 13 times 10 to the 6th newtons per meter squared. So if we look at this graph now, 13 megapascals, we can see that 13 is somewhere down here, 13 megapascals. So we know it's in the elastic regime. So we need to know now what the Young's modulus is. And here is kind of a tricky calculation, because clearly there's a steep slope here and then a slope that drops off here. So is it the steep slope or is it this one? You might say to yourself, well, the experimental data show it's the steep one. I mean, clearly in the beginning here, at 13 megapascals, you're going to be very little strain. So we could use this as the original. We can kind of call this a triangle from here and compute this. We could say this is about 50, the Young's modulus is equal to 50 megapascals divided by this strain here, which is, this is 0.05. I call that roughly 0.005 strain, no units. So that makes that 50, see, 5,000 divided, 3 divided by 5 is approximately, is that right? 5, I'm moving that 1, 2, 3, so 50,000 divided by 5 is 100,000 megapascals, which is about 100 gigapascals. Now, that is 100 gigapascals is on the order of the Young's modulus that you'd expect for steel. So let's use this as the value for this computation, 100 gigapascals. So we have that the stress equals sigma times epsilon, and we are computing the strain is 13 times 10 to the 6th newtons per meter squared. Oh my gosh, this is impossible to read. 13 times 10 to the 6th newtons per meter squared divided by 100,000 times 10 to the 6th newtons per meter squared. So this is equal to 13, this kind of cancels out, 10 to the 6th, 10 to the 6th, 13 over 100,000. So that's, let's see, what is that? 13, that's 1, 2, 3, 4, 5. 0.00013 is equal to the strain. And to compute the delta L, we take that strain and multiply it by the original length, which is 50 millimeters. I'm running out of space here, I see, so I'm going to erase some of this. I see that I can't. So let's just take, that's my dog, 50 millimeters times 0.00013, and I'm just doing this in my head. Oh, God, my dog. This would be .0 this times 100. That means move this way, 100. That divided by 2. 0.0065 millimeters. Is that right? I'm going to call it good. There's 100. So I said the same thing. 50 is 100 over 2. So I multiplied that by 100, moved the decimal 2 places, and then divided this thing by 2. Yeah, okay. There it is. 0.0065 millimeters.